In Lesson 2.2, you can see that our title today will be working with graphs and using a visual representation of growth. So you can see our lesson aim there is to interpret growth rates displayed by graphs. So before we get started, I thought a quick review of graphing. I'm sure hopefully this is going to be a review for you. But let's just take a quick look at a sample graph, and we'll identify the type of graph in just a minute. But here I have a table of values, and the day, typical fashion, the first column represents the x coordinates of ordered pairs. We call that the independent variable. And the second column would be the y coordinate of an ordered pair, and we also call that the dependent variable. So as I'm plotting the point 1, 3, on day 1 we sold 3 vehicles, so that would be this point right here. The point 2, 6 be right here, and then the point 3, 5, and the point 4, 2. So we just did a visual representation of the data that was provided in this table. But something that's very important, I left off of this graph on purpose because I want to make a point, is when you are graphing table data, please make sure that you provide labels for the axes. We have a horizontal axis, typically call that the X. That will be where our independent variables are. And then we have this vertical axis we typically call the y-axis, and that's where the dependent variables are located. So in this particular case, I want to provide some context. Without labels, this graph really is meaningless. So I'm going to put the day along the horizontal axis, the x coordinates, and then number of vehicles sold to identify what these numbers represent. Alright, so just a quick review of graphing, and as we're going to see on the next slide, this is actually a type of graph called a scatter plot. That's a really basic one, and typically scatter plots will have many more data points than this, but a scatter plot is very simply just taking our values out of our table representing ordered pairs and just plotting them accordingly on our graph. Okay, so with that said, let's do some definitions as we make our way through this lesson. A graph, scatter plot, is a graph consisting of adjacent, wrong slide, isolated, I was looking at the wrong blank there, sorry about that. Isolated, meaning they're not connected, with each dot corresponding to a data point. And these are helpful in certain cases, and I've listed those for you. The values of the independent variable, again, that's the x-axis, are not evenly spaced. If those values are evenly spaced, then a bar graph would probably be a better option. They're also helpful when you need to represent a large number of data points that cannot be reasonably displayed with a bar graph. Sometimes scatter plots can contain hundreds of data points, and they are better when we're dealing with a large number of data. And then you are looking for patterns. They are helpful when we're looking for patterns in the data. Alright, so our first example here, we have a table, and I went ahead, and you'll do the same thing on your assignment. You'll sketch out this basically quadrant 1 of the XY coordinate plane, and I've predetermined, you'll do the same thing, go ahead and come up with an interval to separate the values on each axis. They don't have to be the same interval, but make sure you predefine the interval, and then you're going to plot in and around your two axes as you have them set up. So the x-axis is the length, so I'll just estimate 3.5 and then 8.2. Again, just your best guess on where you think that should be. And then 6.3, 15.7, a little bit higher. 9.4, 24.0. 9.8, 24.9. Those are really close together. 24.0, just about halfway. 65.6. I'll call that right there. And then 47, 95.1. So we'll just come up here and we'll guesstimate that to be there, maybe a little bit higher than that. But that is a scatter plot. So really do not connect them. If you're asked to make a scatter plot, you just plot the points, leave them unconnected or isolated, and there you have it. And again, just a reminder, make sure you label the axes accordingly. Alright, now we move to a line graph which starts with a scatter plot, but then we're going to join the adjacent points with straight line segments. So this is the previous scatter plot that we drew. And to make a line graph, very simple, we just take those points and we connect them with line segments. Like that. And so there's one big advantage, and I've provided that for you here at the bottom. If we wanted to know in this information how fast a 15-inch long animal can run, well, if we're just looking at the data presented and looking at the graph in scatterplot form, we don't know what that is. But with a line graph, we can estimate that because I can go to 15 and I can go up to that line where x equals 15, and I've got a pretty good idea now where I really didn't have before. So just about 40, a little less than 40, is the running speed for an animal. 40 feet per second is the running speed for an animal that is 15 inches long. So just wanted to highlight that advantage that stands out for line graphs over scatter plots. Okay, well, here's an example for us to do. Here's the table, and let's make a scatter plot, and then we will turn that into a line graph. So looking at our age in days, so I'll go ahead and label the x-axis, and I have a low value of 5 and I go up to a high value of 70, so I'm just going to make these in intervals of 10. And then for the height in centimeters, low value of 17 all the way up to a high value of 231, so I'm going to choose 50s as my interval for the y. And 250 should capture that high value. And now it's just a matter of plotting. So 5 days would be about right here, and then just up a little bit to represent 17.43, 35, and then just a little bit above 100, just barely above 100, 41, and then 128.68. See right there, 61,209, so just a little bit above 200. Now you are welcome to go ahead and extend lines across like this if it's helpful. Might give you a little bit of better reference point. And then 70 to 31.23. We'll say that's right there. So we have done the scatter plot of the height of a sunflower as a function of its age. And then to do the line graph, we just connect those with line segments. And there we go. So that is example number 2. Okay, now we move to our next point in our notes, interpreting line graphs. There's really 2 ways of interpreting, and we'll talk about those in just a second. But a key feature of a line graph is that they display maximums and minimums as well as growth rates. So here we have a table of values that basically gives us information about the 5-year cancer mortality rates of different male, female, and then black, white people during a certain time period. And you can see looking at our graph, and we always interpret graphs from left to right, just like you read. So let's just take this top curve line graph, and that represents black males in this study. So you can see that from left to right, this line graph is, think of it as a positive slope. It's increasing, or we would say it has positive growth from 70 to 74 until it reaches 1990-94. At that point, it becomes negative growth or decreasing. Those are synonymous. So there's 2 things we're looking at here, positive or negative. Just think positive slope, negative slope. And then at what rate is it increasing? So the steeper the line, the faster the growth. And then the flip side of that would be the flatter the line. We'll use the next one as an example. The white males are increasing, but at we would say they're increasing at a decreasing rate, not really a fast rate at all. And then when it hits, 90 to 94, it shifts to decreasing, and it's more of an increasing rate. It's a little bit steeper on the other side of 1994. So the bottom line here that we're trying to get across is really there's 2 ways of measuring growth when we're looking at graphs. We want to know the rate, and that's determined by the steepness. Steeper graphs, faster growth rate. Contrast that with flatter graphs, that means slower growth. And then an increasing graph indicates a positive growth rate, and decreasing graph is a negative growth rate. And we always look from left to right when we're analyzing these graphs. All right, so let's take a look at our next example. The graph below shows sales in thousands of dollars from 02 to 11. Describe the rate of growth in sales over that period. Okay, so we'll just kind of take these. There's really 3 separate periods here that we look at. The growth rate was negative, so this is a typical answer that you would give. Tell me where it's positive or negative, or may have growth of 0. So it's negative between 2002 and 2006, and between 2008 and 2011. Then those are both negative growth, but one is, we would say, more negative. One is steeper than the other. So we would say the growth rate was more negative, or I'll just say it was more negative growth rate between 08 and 11. And then finally we have this piece here, and that's just horizontal, so there was 0 growth, or we would say the growth rate was 0. And that's between 06 and 08. So that's the way you're going to use words. Make sure your complete sentences, just like I did here. That's a good example when you're analyzing growth, looking at a graph. All right. And then our final type of graph is called a smooth line graph. It's also made from a scatter plot, but now we're joining data points smoothly with curves instead of line segments. And these are most commonly used. They're appropriate when the rate is continuous. So in other words, using our previous example as an example, we had a period where we had growth of 0. A smooth line graph would be, it's always decreasing typically, or it's always increasing. You don't have any of these intervals where it's maybe changing from one to the other. It'll always be going in one direction, either positive or negative. So here's an example, cleaning out a toxic waste site. Typically the amount of waste eliminated decreases over time. That makes sense, probably because, well, in class I just used the example, maybe we have 15,000 tons of waste that we started with that's removing, and I'll just come up with a, yeah, I'll just use the 15,000. All right, and time we'll just say in days. All right, so just to give us a little bit of context, we started at the beginning of our removal process, so at 0 times 0, there was 15,000 tons of waste that needs to be removed. Over time, as days passed, that amount is decreasing, and it's decreasing forever. However, as we're going to reach a certain point where there's less and less waste to remove. So I started off, we're going at a pretty good clip, but eventually I've got fewer and fewer tonnage of waste, and so this graph is going to flatten out a little bit until eventually it's going to get to 0. So we say that it's decreasing at a decreasing rate. It starts off pretty fast because we've got more of it, but as we remove more, obviously there's less of it remaining, and so we are removing fewer tons of waste as the days get bigger, and then eventually, if we do the job correctly, we're going to get to zero. But that's an example of a smooth line graph. It's always either decreasing or increasing, typically, and those are when they are used most often to describe these kind of scenarios. All right, so let's go to number 8. The graph below shows the results of studying deer population on the George Reserve in Michigan. Give a brief general description of how the deer population changes over the 10-year period. Well, it's growing for the whole time. But it grew at different rates, some a little faster than others. So the population grew, I would say, throughout the 10-year period. It's always positive. Over the first 4 years, it's increasing population is increasing at an increasing rate. You can see it's a little steeper. After year 4, it seems like year 4 is kind of like a turning point in calculus. This is referred to as an inflection point. It's kind of like after year 4, things start to change. It goes from, you can kind of see it's concave up, meaning use the phrase up like a cup. It's not very pronounced, but you can kind of see it. And then after year 4, it flips over down, the phrase down like a frown. So it's kind of like year 4 is where that change happens. So after year 4, the population is still increasing, but at a decreasing rate. Sorry, my writing is sloppy. And then as we get to the end, as we're approaching year 10, the graph flattens. So it's still growing. The population is still growing. Sorry, it flattens. Graph flattens as we approach year 10. And that shows that the population is leveling off, staying at about 175 deer. Something to that effect. And then I think we've already answered this question. Estimate the time at which the population is growing at the fastest rate. And we would say that's right here, where after year 4, the rate started to change. So I'm going to say year 4 is the time at which it is growing at its fastest rate. It's at its steepest at year 4. Okay, so that takes care of our notes. And now you have your assignment to do, practicing what was talked about in this lesson. So you'll see the answers provided for you. And if there's anything I can do to help you with that assignment, please let me know. And I will see you next time.